Hello everybody, welcome back to our class BJTE 2023 Electric and Electronic Technology. Today we will look at new chapter 7, which is power. In addition to current, voltage, and resistance, a fourth quantity is important in circuit analysis. This quantity is called power. Power is the rate at which work is done. Every time a circuit is energized, power is expended. Power is directly proportional to both current and voltage. This chapter looks at circuit applications involving power. Electrical or mechanical power relates to the rate at which work is being done. Work is done whenever a force causes motion. If a mechanical force is used to lift or move a weight, work is being done. However, force exerted without causing motion, such as a force of a compressed spring between two fixed objects, does not constitute work. Voltage is an electrical force that creates current to flow into a closed circuit. When voltage exists between 2 points and current cannot flow, no work is done. This is similar to a spring under tension that produces no motion. When voltage causes electrons to move in a circuit, work is being done. The instantaneous rate at which work is done is called the electric power rate and is measured in watts. Power can be defined at the rate which energy is dissipated in a circuit. The symbol for power is P. The total amount of work done may be accomplished in different lengths of time. For example, a given quantity of electrons may be moved from one location to another in 1 second, 1 minute, or 1 hour, depending on the rate in which they were moved. In all cases, the total amount of work done is the same. However, when the work is done in a short period of time, the instantaneous power rate, wattage, is greater than when the same amount of work is done over a longer period of time. As mentioned, the basic unit of power is the watt. A watt is equal to the voltage across a circuit multiplied by the current through the circuit. It represents the rate at any given instant in which work is being done, moving electrons through the circuit. The relationship of power, current, and voltage may be expressed as follows. P equals I times E. I represents the current through the circuit and E represents the voltage applied to the circuit being measured. The amount of power will differ with any change in the voltage or current in the circuit. Example, calculate the power consumed in the circuit shown in figure 7.1. Given in the figure, current, I equals 2 amps and voltage, E equals 12 volts. We need to find the power, P. Using the formula P equals I times E, we get 2 amps times by 12 volts. This will give us a value for power, P equals 24 watts. Example, what voltage is required to deliver 2 amperes of current at 200 watts? For the example, we are given current, I equals 2 amps, and power, P equals 200 watts. We need to find voltage, E. Using the same formula P equals I times by E, we rearrange the formula to voltage, E equals P over I. Substitute values. We have V equals 200 watts over 2 amps, which is equal to 100 volts. Example, how much current does a 100 watt, 120 volt light bulb use? From the example, we have power, P equals 100 watts and voltage 120 volts. We need to find the current, I. By rearrange the formula, we get current, I equals power, P over voltage, E. Put in the values given, we get current, I equals 100 watts over 120 volts. This will give a value of 0.83 amps. Power application, circuit analysis. Resistive components in a circuit consume power. To determine the power dissipated by a component, multiply the voltage drop across the component by the current flowing through the component. Power, P equals current, I, times by, voltage drop, E. The total power dissipated in a series or parallel circuit is equal to the sum of the power dissipated by the individual components. This can be expressed as, total power, PT equals power at R1, PR1 plus power at R2, PR2 plus power at R3, PR3 plus until power at Rn, PRn. The power dissipated in a circuit is often less than 1 watt. To facilitate the use of these smaller numbers, the milliwatt and the microwatt are used. 1000 milliwatt equals 1 watt. Therefore, 1 milliwatt equals 1 over 1000 watts. Meanwhile, 1 million microwatts equals 1 watt. Therefore, 1 microwatt equals 1 over 1 million watts. Example, how much power is consumed in the circuit shown in figure 7.2. First step, we need to determine the total resistance in the circuit. Since the resistors in the circuit are arranged in series, we can sum up all the given resistors to find the total resistance in the circuit. Therefore, total resistance equals R1 plus R2 plus R3, which is equal to 2380 ohms. Second step, we need to determine the current flow in the circuit using Ohm's law. Total current equals total voltage over total resistance, which is equal to 0.005 amps. The last step, we need to find the power, which is equal to total current, IT multiplied by total voltage, ET, which is equal to 0.06 watts or 60 milliwatts. Example, what is the value of resistor R2 in the circuit shown in figure 7.3? The first step for this example is to find the voltage drop across the resistor R1. Given at R1 our current equal to 1.5 milliamps and power equal to 18 milliwatts. By using the power formula, P equals I multiplied by E, we get voltage drop, E equals 18 milliwatts divided by 1.5 milliamps. This will give us a value of 12 volts. The second step, we can determine the current across resistor, R2. We know that in parallel circuit, voltage are all equal. In this case, all voltage are equal to 12 volts. Therefore, we can determine current at R2 by using power formula. Current at R2 equals power at R2 divided by voltage drop at R2, which is equal to 0.00217 amps. Then, the last step, we can determine the resistor, R2 by using Ohm's law. R2 equals voltage drop at R2 divided by current at R2, which is equal to 5530 ohms. Example, if a current of 0.05 ampere flows through a 22 ohm resistor, how much power does the resistor dissipate? The first step is to determine the voltage drop across 22 ohm resistor using Ohm's law. Voltage drop is equal to current of 0.05 amps multiplied by 22 ohm resistor. This will give us a value of 1.1 volts. The second step, we can determine the power that dissipated at the resistor using power formula. Power dissipated at resistor equal to current of 0.05 amps, multiplied by voltage drop of 1.1 volts. This is equal to 55 milliwatts. Thank you for listening to the presentation. If you should have any question, please feel free to ask. Thank you once again.